So the lower one, this is the 2310 test.
We're going to start with the CMOS synthesis. So this was one of the first ever most simple circuits that you could find. It's a transistor level. So there are two kinds. The first one is NMOS that you conducts when the control input is 1, and the opposite, that's a PMOS that is the same, but it does control input when it's a 0. And the CMOS is basically a combination of these two. And yeah, I have a couple of examples that are gonna go. So this very simple. This explains when A is equal to 1, then the one below will go there, right? And the while output is 0, and it will be the opposite when it goes up. So more complex examples that we find, maybe in the test probably, if I remember correctly. So the inputs are given to you. The example is like that. The A, can I do that? Okay. The A is equal to 0, and all the A's are given, right? And for example, 0, since we see it's a PMOS, it goes through, and since up here is the 1, they can, so.
No.
Almost that. Yeah, so it goes through all the way to J, and since P is also equal to 0, it goes through again, this again, right? So since J is a 1, we have a keep making stuff, but what is this? At the bottom of the line, it goes through, it's a 1. So you end up going to ground instead of 1, so the output is 6 in this case. So if the inputs are changed a bit, we see that it's not a huge change because it's also A equal to 0, so it's the same output as before. And since this is a 0, this doesn't go through the ground, so it's always a 1 in this case. Again, this is showing you how if A is equal to 1, but still B is equal to 0, the analog pulse they can go through 1 and continue being the same output. So the next topic is the analog versus the digital inputs, and this is going to talk about.
So analog systems are treated as continuous. So circuits being connected, they generally result in amplified voltage as shown on the top of the figure. It's amplified, the input is elongated. And then for digital systems, they are either treated high or low, so on or off, and they tend to be in a square shape. They take an input signal and generate an output signal that are inverse, as shown at the bottom of the figure. And the next topic will be AND gates. Okay, so I'll be talking about the different kinds of gates there are. So the first, like the main three are AND, OR, and NOT. So AND gates, they output 1 only if all the inputs are 1. So if you can see in this truth table, A and B are 0, so Y is 0 because there's not a 1. While the second one, 0 and 1, it outputs a 0 because both inputs have to be 1. On this one, 1 and 1, output will be 1 because both inputs are 1. So it's denoted by multiplication. So when you have an equation and you see multiplication, that's how you know that those two inputs are connected by multiplication. And this is how an AND gate looks like. It has a straight line right here. Okay. So the next one is an OR gate. OR gate outputs 1 if at least one input is 1. So on the truth table, this one outputs a 0 because there's not a 1 in the input. However, this and this outputs a 1 because there's at least 1, 1. And then the last one, 1 and 1, will output a 1 because there's 2 ones. And it's denoted by addition. So in the equation, an addition symbol, a plus symbol will mean an OR gate. And this is how it looks like. There's a curved edge right here. Okay, the last one is the NOT gate, or the inverter gate. The NOT gate basically switches the input. And it has a mark like this or a mark like this. So in the input, if A is 0, the output would be a 1, and then if the input is 1, then the output would be 0. It basically just does opposite. And this is how it would look like. It's just a triangle with a circle on it. And the circle is called the inversion buffer. So we have some examples over here. So the first one, it's an AND gate because it has a flat line right here. So if 2 inputs are 1, that means the input would be 1. For this one, this is an OR gate because it has a curved edge. An OR gate, at least one input has to be 1, which we have, so that means this output is 1. I'm sorry. And then this one is a NOT gate, which is opposite. So since the input is 0, the output will be 1. This one is another OR gate, meaning one input has to be 1, which we have, so that's 1. And then this one is a AND gate, which means all the inputs have to be 1. One of them is 0, so that means it is 0. So you can check your answers over here. And then these are the 3 that you'll learn later. That's just going to be on your first exam. But we have NAND, which is not AND. So this outputs 0 only if both inputs are 1. So it's basically just the opposite of an AND gate. So you can look at the truth table. When they're both 0, it outputs 1. When there's only 1, 1, it outputs 1. Okay, so then you have your NOR gate, which is not OR. The output is 1 only if both inputs are 0. Otherwise, the output is 0. Okay, and then you have exclusive OR XOR gate. This outputs 1 only when an odd number of its inputs are 1. So on this one, there's an odd number of inputs that are 1, so the output is 1. And then you have XNOR or exclusive NOR. This outputs 1 only when its 2 inputs are equal. So these ones, they're good to know, but I don't think they're open as an exam 1. So the main thing you have to focus on is AND or NOT. Okay, so now we're going to get into drawing some circuits. So we have convert A plus B naught times C naught plus D into a circuit. So the best way to deal with this is taking it part by part. So first you have A plus B naught. So that means you would have an input A, and then you have B naught, so you have an input B, and then you have to knot it. So to knot it, you do a triangle with an inversion bubble, and they're connected by a plus sign. So a plus sign means OR. So you would do a curved OR gate. Okay, and then we look at the second part of the equation, C naught plus D. So you would have a C naught. So C, and then you would knot it. And then plus D. So it's joined together by plus, so that means these 2 inputs have a sort gate. And then the way to connect these 2 is based on right here. So you can see that they're multiplied together. A plus B naught is multiplied by C naught plus D. So multiplication means AND. So that means these 2 would be connected by the AND gate. Like that. So this is B naught, this is C naught. Okay. So that's how this one would look like. And then here's an example 2. I gave the answer for this one. I just wanted to go briefly how it can get confusing. So this knot right here is only for this BC right here. So you can see that in this diagram, BC is connected by this knot. So whenever you're on the test, you always have to be careful and see where the knots are for each part. And this knot knots the entire equation. So I do that over here by this knot. because it ignores the entire equation. Also, we might see something like this. So, this basically means that there's another input B that goes to this gate, but it's not knotted. So see how the circle is before the knot? That would mean that the knot, this gate is not knotted, like this. Okay, example 3, turn the circuit into an equation. On this one, just again, go gate by gate. So first we have A, which is knotted, so A knot, and then we also have a B input, and you can see that they're joined together by an OR gate, so A naught plus B. And then you have another gate over here. You have B and C, which are connected by an AND gate. And then you just have a knot right here, so that means this part of the problem would be knotted. And then these two parts are joined together by your AND gate, so that means if you multiply. So your final equation would be A naught plus B times BC naught.
Thank you. So we're gonna go ahead do the Boolean theorem. So I'm just quickly gonna go over all the theorems. So the identity is just basically if you multiply it by 1, we get the same variable. And then for or, if you add 0, it's just the same thing. And then complement. So complement basically means if you multiply the complement, you're gonna get a 0. And then if you add the complements, which means if it's either 1 or 0, if you add them up, you get 1. Null events, null element just means if you multiply it by 0, you get a 0, and if you add 1, you would get 1. And then idempotent, it basically means if you multiply the same variables together, you don't square it like algebra, it's the same thing, so just A. And then same thing, if you just add them up, you just have one of them. And then involation, it just basically means if you're knotting it twice, you're going back to the original. So yeah. And then the other theorem, so the distributive property. So for addition, you just distribute it like this. So it's A, B plus C, right? So you just do AB plus AC. And then for OR, it's the same thing. You would do this whole thing, the A and the plus distributed. So it'd be A plus B times A plus C. The cumulative property, it just basically means it's the same thing. However you multiply it, however you add it, you're still gonna get the same result. The associative property, it basically means that however you multiply it, regardless of like how it's multiplied, if you multiply the A and the B first and then C, or the other way, if you multiply A and the BC first and then A, you'd still get the same answer. And similarly, if you with the addition, it's the same thing. The next big thing is the De Morgan's law. This basically means is when you're knotting it and you have an addition, you change the addition to multiplication and you knot the elements individually. And then it's the opposite for the OR gate. So if you're multiplying it, the multiplication turns into addition, and each of the variables become A naught and B naught. So we can go over the example. So the example is A plus B naught C times A naught B plus C. So we can, and then the rest of the equation. So the first, what we can do is we can take this, this thing, and we can separate it but individually. So we can do it like this. A times each of them. Wait, sorry. Tessa, how do you erase it? Sorry. Oh, okay. Thank you. So what we're doing is we're basically taking each of these elements and we're multiplying it with the whole thing here. So we're doing A times A naught B plus C, and then the same thing here. The B naught C times the whole thing. And then we're gonna leave this not for now. So that's the distributive property. We distributed the first set of variables into the second one, and we simplify it. So we just do it again. This is again distributive here, distribute it here, so we get this. And then for this one, since we have a not here, we know it's going to be we're going to use the De Morgan's law. So here we have addition, so it becomes multiplication, and we not each of the elements inside. So it'd be AB, the whole thing knotted, times C double knot. And then, and as we learned before, if it's double knot, it just it becomes it just becomes C. And then oh yeah, okay, so we're just doing this is here, this is here. So for this one, since we have A and A naught, it just becomes 0 because of the complement. So that's just 0. And then we just have AC left over there. And then the next one, when you multiply it, this is, again, we have the complement again here. So that becomes 0. And then we're left over with B naught C. And then the last one, we have the C here, then it just becomes C. And then if you go here, we have knotting this thing, so we use the De Morgan's law again, and then so the multiplication becomes addition, and we knot each of the individual components. And then we have the double complement, which is just, if you have two knots, we just go to the original C. So from here, we have AC. We have the AC here. We just took out the C from here and here. So we just do C times A plus B naught plus C times A naught plus B naught. So let's go to the second one. For this one, we're just inversing the whole equation. So we can go one by one. So for the whole thing first, these are the elements by themselves in our first De Morgan's law. And we know we're doing multiplication, so we change them to addition here. And then we knot the whole element. And then we can continue it again and again. So this whole thing is knotted, this whole thing's knotted. And make sure you show all of your steps. And then same thing here. For this one, we're knotting it and we have addition. So we multiply each of them and we knot each of the components. So the A, it's already knotted. So we do it again. It becomes A. B is done. We're doing it twice, so just B. C, it's only once, so it's C naught. Same thing for the other two elements. They're all addition. We multiply it and then we distribute the knot. So the A just knot, the B has twice. So similarly, we do it for this one and then we get the answer. And so let's go to the next one. So the sum of products and the product of sums. So let's get some vocabulary first. So literals, they're basically variables in both their true forms and their complement. So it's the A and the A naught in all of the variables. And the canonical, it basically means that whatever our product or the sum is, we have all of the variables, so all of the literals. So let's go one by one. So the sum of products. So as it says, sum of products is we have multiplication and then we add with another multiplication of variables. This is basically where the function would result 1. So that means all of our true variables, they're going to be 1, and all of our complemented variable are going to output 0. And the min terms are basically the sum of products, but with all of the literals. So for this example, this is a sum of products, but since it's missing some of the variables, like it's missing an A here, it cannot be a min term. But if it has all of the variables, then it's a min term. Similarly, for the product of sums, this is where the function would yield 0. So it's basically the opposite of our sum of products, where the true variables are 0, the complements are 1. And this is associated with the max terms. So max terms are basically product of sums with all of the literals. Similarly, in this example, here we don't have an A, here we don't have a C. So they cannot be a max terms, but they are a product of sums, just because there's a product and each of the elements are added together. And here's the example of max terms, which is where same thing, they're product of sums, except they have all of the literals in it. Here. So again, just to rephrase, right? Sum of products, it's where F would be 1 and max terms are when F is 0. And here's an example. This is min terms. So although we don't have anything addition, we can assume it if you add 0, right? So that's addition and this is multiplication. So this is min terms. And here, multiplication here. So we're producting and there's sums here. So this is max terms. Also, it's max terms because we have all of the literals. So we have A and B in every single element. And so the compact notation, this is basically, if you remember our table, truth table. So here, let me draw it right here. So we have some for 4 variables. We have A, B, C, D. So we have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. And I know you guys don't know all the others. These are basically, this is, if you turn it in from binary to decimal, this is 0, this is 1, 2, 3. So it just goes down until 15 because we started with 0, right? So there's 16 of them. So in the compact notation, what we do is basically each of these, right? We can convert this if we do max min terms from, so here. Min terms, it's where the literals are ones. So for this one, if we do this, right? So it would be A not, B not, C not, right? And D would be not, it would, since it's one, so D would be the true variable. So here would be A naught plus B naught plus C naught plus D, right? So this is where this is going to yield 1. So that's the min terms, and in the compact format we have the summation, and then for min terms it's the small m, and each of the numbers, these numbers are associated with which line of the truth table it is. And then similarly for max terms, we have the symbol is this with the capital M, and then all of the numbers of the line here of the truth table which associate to, that would result 0. And so here for this equation, we can write the compact notation. So this is a sum of product, right? Because we're summing the product, so it's a min term. So min terms, if you remember, the normal numbers are 1. The complement is 0. So this one, if we just do, it'd be 0, 1, 1. This would be 1, 1, 1, right? So if you go back to the truth table, or if you just want to, an easier way is just you just find the decimal value. So this is 3, this is 7. So the compact notation would be 7. And then the conversion. So if we're trying to convert from a sum of products to the sum of min terms, we're basically, what we're trying to do is, this basically means that it's already in the format of our sum of products. It just means we need to make sure each of the elements have all of the literals. So what we can do is we can just multiply whatever term is lacking. So whatever term is missing, right? We can just multiply it to the whole variable. So to go from here, we know so go from here, it's a 3 variables, so we're missing the z, right? So what we can do is we can multiply this by 1. And if we remember from our theorems, we can do to 1, we can just do a plus a naught, that's still 1. So if we go back to our example, here we can multiply this with z plus z naught. This is basically we're multiplying it by 1. We're just in a different notation. And then we can do the distributive property. So we do z plus w naught. So this is a sum of product, but it is also a min term because we have all of our variable in each of the elements. And the same way, if you want to go from a product of sum to a product of max term, what we do is we basically add it by 0. And if we remember to add it by 0, we can multiply it by y, and in this example, it'd be z and z naught. This is basically 0. We're adding it, so we can do this. Okay, sorry. Here we're not using z, so we're using x. Let's do x and x naught. So then we can distribute it, the whole thing. So it'd be w plus y prime plus x times, we distribute the whole thing to the x naught. So w plus y naught plus x naught. So that's the answer. And here's another example. So if we want to convert it from a sum of product to a product of sum, what we can do is we can apply the De Morgan's law to get f prime. So right, so we're doing this because as we know, if we do the De Morgan's law, we can change the addition to multiplication. So this is going to be a naught b naught times b naught c naught times c naught a naught. And we can just do this again, De Morgan's law again. And we can do De Morgan's law again. So it'd be a, since it's double naught, we just eliminate it, times b plus c naught. Again, this is twice naught, so just b times c naught plus a naught. So we converted it from a sum of product to product of sum. And then for this one, we can do it algebraically, or what we can do is there's an easier way to do this, is we can just do it using a truth table. So if you remember max terms, right? So this is where the literals are zeros and the complements are 1. Here I can show it. So they're zeros and they're 1s. So what we can do is so this would be 0 0 0, be 0 0 1 0 0 0. This is just repeating. That's fine. 0 1 1 1 0 0. So now what we can do is in the truth table, where we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1. Right, right? And so 0, 0, 0. So this is a max term. So this is going to yield 0, 1 is 0. It's 0 again. So just repeating, that's fine. So this is also 0. These are max term values. And then this is also max term, right? So since these are max term, that means this one and these 4 are min terms. So we can just look at these numbers. So let me just write it down. So 0, 1, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So these are going to be the min terms. They're min terms because we found the max terms. So whatever the max terms are, the remaining are going to be the min terms. So we can just, and if you remember, min terms is just the opposite. So the literals are 1 and the complements are 0. So if it's 0, so it's A naught, sorry, I keep on saying A, but I meant X naught, Y, Z naught plus, because we're doing sum of products. A, sorry, I'm so used to A, X, Y naught, Z plus X, Y, Z naught plus X, Y, and Z. So that's the answer. That's the easiest way. You can change it from a sum of product to a product of sum. You can also use the same way of doing it in this equation, but I think if you do the algebraically here, it's easier and I guess you're more guaranteed to find the answers. But if you think using the truth table is easier, you can definitely do that. But I think sometimes the professor is going to ask you to show your work, so it's better to do it this way. And then, yeah. Oh, sorry.
Yeah. So next topic is the timing diagrams. You'll probably be given a function like this. Like this. So first you need to try and find the truth table from there. Yeah, so we do the same, the 0, 0, 0, 0, 0, 1, we know all that. And from the equation, 0, laser,
This one's the eraser.
laser,
Oh, laser. Sorry. Oh, sorry.
Laser, okay. So yeah, from the truth table now that we have all this, as we always do, we check the equation. It's this one, right? So as they explained it before, if they're multiplying their and there's adding it or so we look at the first term, it's A times B naught. So the A is a 1, in this case, the B naught is a 0. So we check where the A's are 1s and then the next where the B's are 0. So these two terms, this will be 1 for the F, the ending, this is the output, right? So now that we have these first two outputs for the first term, we change to the next one, which is the B has to be 1. So either these two or these two. And C has to be a 0, right? Because it did not. So we have this one and we have this one, right? So we end up having these 4 outputs for the F. So now this is the first step from the equation to the truth table. Now we have to plug it in. So this, you're gonna come out with this from the truth table. That should be pretty simple. The clock is always happening and it's usually half cycle. The A, half of it is 0, so half of it is 0, and then half is 1. Then the B is goes like this, and then the C happens every single cycle. So that should be the first step. So when we are adding output at the end, we check every single state. We start from Okay, we roll. Let's see this one. So here we have the output in the timing diagram here, the truth table. So the first day is 0. Because it's right there, so whatever. Oh, it's 0, then the next second step is 0 again. Then we take the it's a 1 here. So it's a 1. The next one's a 0, so we go low again. Like 2 1s, so 2 states are 1. Another state is 1, I messed that up. So we continue another one. And then the last one is 0. So that's how from the truth table to the timing diagram. Now you should be also able to go from the timing diagram to the truth table, right? It has to be both ways because they can ask you, hey, come up with the truth table or come up with the equation from the timing diagram. So that really is important to go the 3 ways every single direction. So yeah, this is the answer. Yeah, the base conversion.
So the next part of the review is going to be over base conversion. And there are 4 different ways to express this. It's a decimal, which is shown up with base 10. Binary, which is 0, 1, which is base 2. Octal, which we won't be using, but it's just base 8 and 0 to 7. Hexadecimal, which is base 16, which is 0 to 9, and then 8 to F. The main ones that you'll probably need to know for example are circled. So first, binary to hexadecimal. So when you're given binary, the first thing you need to do is split into 4 digits. Over here, you've already given 1011, 0111, and then you've divided into 4 individual bits, and then you convert each individually. So this is 2 to the power 0, 2 to the power 1, and then 2 to the power 2. That's 4 plus 4, which gives you 7. Over here, you do the same exact thing, 2 to the power 0, 2 to the power 1, and then 2 to the power 3, which is 8 plus 2 plus 1, which will be 11. But in hexadecimal, it goes through 0, it goes through 0 to 9, and then after that, it goes through 1. So 11 is first one. And then the next part is hexadecimal to decimal. So you would do the same exact thing. You're given hexadecimal, and you would take the first digit to the right and put that to the power 0. And remember, hexadecimal is base 16. So this would be 16 to the power 0, 16 to the power 1, 16 to the power 2, and 16 to the power 3. But you can multiply by each individual values. So 1 would be multiplied by 16 to the power 3, and B corresponds to 11 in hexadecimal. So it would be 11 times 16 to the power 2, and 7 times 16 to the power 1, and E corresponds to 14 in hexadecimal. So it would be 4 times 16 to the power 2. Now for hexadecimal to binary, again, you would take the individual values. So this is a conversion of AN into binary. A is 10 in hexadecimal, so you convert 10 into binary, which is 1010. Is 2 to the power 3 plus 2 to the power 1. And then you are given 9, and you just convert 9 into binary, which is 2 to the power 3 plus 2 to the power 0. You won't need to do no octal at all for this exam. But for the next 2 base conversions, you need no decimal to hexadecimal. So once you're given a number, for this example, you're given 445. To convert to decimal, you have to divide by 16. And whatever remainder you get out of this division, that is what you write towards the side and say, okay, 13 is converted to D next hexadecimal. And then whatever 445 divided by 16 gives you 27. You divide 27 by 16 and you're given a remainder of 11. You write that to the side. 11 equals to B in hexadecimal. And 16, the 27 divided by 16 equals to 1. So 1 divided by 16, you can't really divide that. So your remainder will be 1. You write that to the side. And then you read up. So the answer will be 1, B, and D in hexadecimal. Now, the same sort of logic goes for binary. You're given a binary, you give a number, and you convert it to binary, divide by 2, because binary is base 2. 10 divided by 2 has 0 meters. You write 0 to the side. 5 divided by 2 gives you 1. You write the meters to the side. Again, 10 divided by 2 is 5. 5 divided by 2 will give you 2. And then the 2 divided by 2 is the total number, 2 by the side. And then this should one here, but 1 divided by 2 it can go through, so your remainder will be 1. Your remainder will be 1. So when you read it up, your answer should be 1, 0, 1, 0. So the next thing that we're going to be going over is binary addition. So binary addition is similar to adding just regular decimal numbers. An important thing to remember is to line up the bits correctly because that's where it can get confusing. And just some rules: 0 plus 0 is obviously 0. 0 plus 1 is obviously 1. 1 plus 0 is 1. But in binary addition, 1 plus 1 is 1, and then you carry a 0. And then 1 plus 1 plus 1 is 1, and then you carry a 1. So it should look something like this. And you add, you have the carries at the top, and then you might have a leftover carry as a sum. So I'll show you guys an example. We're going to add 183 and 79 in binary. So the first thing we have to do is convert 183 into binary. So the way you would do that is like use the divide by 2. So you do 183 divided by 2, and you guys will get a calculator on this exam, so don't worry too much about this calculation. But 183 divided by 2 is 91, and you'll have a remainder of 1. And then you'll take this and then do the same thing here. So 91 divided by 2 is equal to 91 divided by 2 is equal to 45, remainder 1.
Here, I can convert mine on.
Okay, so 91 divided by 2 is 45, and then you have a remainder of 1. And then you do 45 divided by 2 to get 22, remainder of 1. So whenever you're doing decimal to binary, always keep in count of all of your remainders. So then you have 22 divided by 2, you have 11, remainder 0. 11 divided by 2, 5, remainder 1. 5 divided by 2, you have 2, remainder 1. 2 divided by 2, you have 1, remainder 0. And then 1 divided by 2 is 0, remainder 1. So to write this into binary, you go from bottom to top. So you would have 1, 0, 1, 1, 0, 1, 1, 1, 1. So this would be 183 in binary, and it's base of 2. If we put 2 subscripts here. Okay, so then we'll do 79 in binary. I'm just going to do this really quickly. 10 divided by 2 is 39, remainder 1. 39 divided by 2 is 19, remainder 1. 19 divided by 2 is 9, remainder 1. 9 divided by 2 is 4, remainder 1. 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0, remainder 1. And then go, so make sure you do your decimal to binary conversion until you get a 0. Okay, so then you go from bottom to top. And your final binary value should be 1, 0, 0, 1, 2, and 4 ones, base 2. So that is 79 in binary. So now you calculated 183 and 79, and then you have to add them. So I'm going to write the binary values here. So this is for 183. Make sure you write them with a lot of space in between each bit. That's what makes it easier. And then I'll do this one. And then make sure you line them up. So I'm going to go backwards. 1, 2. Okay, so you can see I have an extra space over there. So what I'm going to do is I'm going to add a couple of extra leading zeros to each one. So 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to go ahead and make it a 10-bit number. So I'm going to have 3 zeros to the end of 70, maybe 10 bit, and then 2 zeros to the end or the beginning of 183 to make it 10 bits. Okay. So then I'm just going to add. So 1 plus 1 in binary is 0, and carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 is 0, 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 carry the 1. And then you'll stop the 1 here and then bring down the 0. So if your number starts with a 0, you can just ignore that. So I'm going to cross this out. So my final answer of 183 plus 79 is base 2. Okay, so that's how you do binary addition. The next thing I want to go over is 2's complement. So 2's complement is a method to represent sum of integers in binary. So you would look at the most left bit, or the MSB, and if the MSB is 0, that means the number is positive. But if the MSB is 1, that means the number is negative. Okay, so negative numbers you can write using this 2's complement. So the way you do 2's complement is you would first write the number in binary, ignore the sign. So if you have -6, you would just write it in binary to 6. And then you would invert all of the bits, and this is your 1's complement, and then you would add a 1 to the inverted number. So this is your 2's complement. So let's do this example. What is the 8-bit 2's complement of -6? So -6, I'm going to write it as 6 in binary. So 6 in binary is 0, 1, 1, 0. So they asked for 8-bit, so I'm going to add 4 more zeros to make it to 8-bit. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So that's 6 in binary, and then I'm going to invert all of the bits. So 0 inverted is 1, 0 inverted is 1, 3, 5, 0, 0, 1. So if you do the opposite of all of these bits right here, you should get this. So this is what's known as your 1's complement. So then what I'm going to do is add a 1 to this number. So once I add a 1 to this number, 1 plus 1 is 0, carry the 1. We're going to bring down this 1, but these all will just stay the same. So this would be what your final answer is of -6 in binary using the 2's complement. And the way you know that this is right is by looking at the MSB. So the MSB is your most leftist value. So if you see right here, our most leftist value is 1. And 1 means that the number is negative. So that's how you know your answer is correct. Okay. So MSB is useful in binary subtraction. So to do binary subtraction, we represent the negative number using the 2's complement. And this is what you would do. If you had a problem, A minus B, you can convert that to A plus the 2's complement of B. It's like in algebra when you have like A minus B. It's the same thing as saying A plus negative B, right? So instead of negative B, you would do the 2's complement of B. And then you drop the carry out bit. And then at the end, always make sure you check your answer by checking the signs. So I'm going to do this example. subtract 79 from 183 in binary. So this is the same thing as saying 100. This is the same thing as saying 189 plus negative, or sorry, 183 plus negative 79. Okay. So we already know the binary for 183. That was 1. That was 1, 0, 1, 1, 0, 1, 1, 1. Okay. So now we have to do negative 79. So to do negative 79, I would have to do the 2's complement. Okay, so 79 in binary, we calculated that earlier. That's 1, 0, 0, 1, 1, 1, 1. So I'm going to turn this into a 10-bit number by adding zeros to the front. Okay. So to make this into 2's complement, I'll first invert all of the bits. So I'll get 1, 1, 1, 0, 1, 1, and there's 1, 0, 1, 2, 3, 4. So I inverted all of the bits, and then I'm going to add a 1 to them. So 0 plus 1 is 1, and then these all will just stay the same. So that would be your negative 79 using the 2's complement. Okay. So now you just do your subtraction, or your, I guess, addition now. So you would do 183 plus negative 79. So if you bring 183 here, so it's 183, and then I'll do plus negative 79. Doesn't line up perfectly. Okay. So this is 183, and this is negative 79. Okay. So do your addition like normal. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. Okay, I'm going to actually line it up. All right. Okay, doesn't line up. Okay. So 1, 0, 0, 0, 1, 1, 0, 1, 1. So that's my negative 79, and as you can see, there's some empty space over here. So I'm going to pad that by adding some zeros. Okay, so 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1, and then 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. And 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, and then you'll have a remainder of 1. So I said on the slideshow, always ignore the carry output. So I'm just going to ignore this 1. And my final is 0, 0, 0, 1, 1, 0, 1, 0, 0, 0. And you don't have to write these zeros, but I'm going to keep them just so I can show that the MSP is supposed to be positive. So when you check your work, 183 minus 79 will get you a positive number, right? So whenever you get your final answer, you know that your answer is positive as well by looking at this MSP. So the MSP is 0, so you know your answer is positive. So that's how you do binary subtraction. So a big thing to remember is again this symbol over here. This symbol over here means midterms or ones. And this symbol over here means max terms or zero. But how I like to remember is min, the opposite of that is one, max, the opposite of that is zero. Right? So the first thing I would do with the K-map is first order the date code. So go from 0, 0, 0, 1. And instead of going 1, 0, you go 1, 1, and 1, 0. The reason why is because only one bit should change. Over here, only one bit is changing. Over here, only one bit is changing. And then over here, only one bit is changing. Okay. But remember the order, and then do the same for the vertical as well. And then you're gonna have to utilize the K-map to write the equations either in SOP or POS form. So SOP is sum of products. So you're gonna be grouping the ones or the min-terms. This is a big thing to remember. As for POS product sum, you're grouping the zeros, which are the max terms. Remember that. And I'll explain more of what this means in the group that is needed in one bit codes needed when I'm grouping the K-maps and the decisions. So the main thing to remember for K-maps are steps. So the first thing I'm going to do is I will create the truth table and then label the K-map with a 2-bit code or the break code I just talked about, the 00 to 10. And then what you do is write the min-terms and ones on the max terms in the K-map. And then you group the min-terms and max terms depending on what the question is asking. For min-terms, it would be SOP, and the max terms would be POS. And then write the expression for the variables that don't change. I'll explain that more later as well. Some grouping rules are that your diagonals don't combine, and you can combine opposite edges of the K-map, and adjacent, not diagonal. And you can only group 2 to part n cells. So that would mean 1, 2, 4, 8. So no odd numbers. And the ideal sort of grouping would be to have the least amount of groupings. Your exam may have different grouping styles, but I would suggest the one which is most optimized or the least amount of groupings. This is the example for the first K-map. So this sigma symbol means min-terms, which are your ones. So you'd be putting the ones in the given location. So remember, this goes from 0, 1, 3, 2, and then over here 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, 15. So the reason why these 2 rows are switched and why these 2 columns are switched is the fact that this doesn't go from 1, 0 to 1, 1. It goes from 1, 1 to 1, 0. So remember where to exactly place your numbers. So given 2, 4, 5, you put in 2, 4, 5, and then 9, 11, 12, 9, 11, 12, and then 13, 14. 13, 14. And once you have your K-map, you put in your min-terms, you can create the equation and start the grouping. So again, you can do powers of 2. So over here, the most optimized version would be to have one grouping of 4 because they're all adjacent. Group opposite edges. And then you group again adjacent. But when you can't group any adjacent stuff like this one over here, or you can't find another min-term to group, you can
Yeah, let's just go back all the way down to. Okay, yeah, thank you. K-maps, and I was doing the POS. So again, I was doing this grouping over here. The A does not change. So it'll be A, and then over here, both C and D don't change. So it'll be A plus C naught plus D naught over here. And then for this, it'll be the same thing, but B is not changing. So it'll be B naught plus C naught plus D naught. And for this last horizontal grouping, the A and B are not changing. So it'll be A plus B naught. And then what's not changing here is C. So it'll be A plus B naught plus C naught. And this is another example on the slides. And you guys can go ahead and do this example yourself. But it's just, again, this sort of square type symbol means it's max terms. So within these positions, you're filling in zeros and you're grouping them. And whatever position is not full of zeros, it'll be full of one. And you can both do SOP and POS equations for those. Again, this recording will be in the Discord. So for the design example, okay. So basically, you have to decide what your input and output variables are, capture the behavior using a truth table, and only when you have the truth table, you'll be able to utilize K-maps to create the equation. And like initially, when we explained how to make an equation, you can make a circuit from an equation pretty easily. So let's look at the designing steps. So first, observe the problem definition. Over here, the question is design a combinational circuit with two inputs which produce an output as logic 0 when any one input is 1. So basically, that means at any point there's 1 in the input, there'll be a 0 in the output. So over here, 0, 0, it has no ones, so the output will be 1. But all the other three has 1 as a single input or both inputs, so both of those would be 0. Now that you've observed the problem definition, know the input-output variables, you already create a truth table, you can create the K-map. So basically, when both A and B are 1s, and one variable is 1 and the other variable is 0, it's going to be 0 on the K-map. So the only time that there's a 1 in the K-map is when both A and B are 0. So if we were to create an SOP of this, it would be, again, y equals to A naught times B naught, because these are the only two variables that don't change. And using that, you can create a logic diagram pretty easily. When there's again a multiplication, that means that it has to be an AND gate, and both A and B are knotted. So A would have an inversion bubble, same thing with B, both inputs, and then it would go into an AND gate. And this also, later on you'll figure out, is also equivalent to a NAND gate. So any tips for the exams I have would be to manage time, be mindful of signs and variables, know where the negation symbols are, and really take your time to understand the question and identify what is being asked. And do not spend extra time in a question. When you do get stuck, switch around, go around the different problems. You're gonna have to do at least 2 K-map questions on the test, and you're also gonna have 1 equation that you have to reduce, and maybe 1 NMOS and PMOS example as well. And again, for those questions that you require simplification, definitely write your Boolean properties, because they will ask you to do so, or else you'll lose points. Okay, you guys have any questions? No? Okay. So we can stop sharing.